Welcome back. In the previous video, we introduced certain key concepts in fluid mechanics, and we looked at a few important properties such as the density, the mass, the velocity, temperature, etc. We also introduced the concept of dimensional homogeneity. In this video, we're going to dig in a bit further into some fundamental properties of fluids, in particular density, mass, and weight. Later on, we'll look at surface tension, and then finally we'll discuss different classifications of fluid flows. The density is defined as the mass per unit volume. Dimensionally, we could say that the density, rho, is equal to a dimension of mass, m, per unit volume, so that would be L to the negative 3. In SI units, this would be expressed as kilograms per meter cubed. The density of a fluid can be affected by temperature and or pressure. So mathematically, we could state that the density is a function of temperature, or the density can be a function of pressure, or both. And again, this depends on our classification of the flow. If a flow is incompressible, for example, then it will not be a strong function of the pressure. If we assume that the fluid is uniform, then we can say that the density is equal to the total mass of the fluid divided by the volume of the fluid. And I'm using this notation for the volume, V, with a line going through it to distinguish it from another fundamental concept in fluid mechanics, which is the velocity, which also uses the variable letter V. But what if the fluid were compressible? What does this mean? If we have a compressible fluid, then perhaps a small volume in one part of the fluid might contain more mass than another part of the same volume. So consider this schematic here. We have a certain volume with 2 points located at x1, y1, and x2, y2. If we zoom in into point 2, what we have is an elemental volume. If the fluid is compressible, then what we would state is that the density at x1, y1 is not equal to the density at point 2. This is the most general description of density. However, of course, for an incompressible fluid, we can make the approximation that the density is constant throughout. So the elemental volume has a volume which we will call delta V. It also has a mass which we'll call delta M. Therefore, the density of this elemental volume is equal to the elemental mass divided by the elemental volume. So we can state this as delta M by delta V. And if we shrink this volume, so if we say that we take the limit as delta V goes to 0, what we are left with is dm by dv. The total mass of a system will just be the summation of all the elemental masses, or the differential masses, if you will. Stated mathematically, we would say that the total mass, m, is the integration of all the differential masses dm. Now we can see from above that dm is equal to the density multiplied by dv. So we can express this integral as rho dv. And this is an integration over the entire volume. So in the most general terms, what we would have is that the mass is equal to the integration over the volume of the density, which could be a function of x, y, and z, and we'll take dx, dy, dz. So we're going to take the integral in all three spatial directions. So this is the most general definition of the mass and how we obtain it from the density, which could be a function of x, y, and z. Let's look at an example where we will calculate the total mass of a fluid in a given volume. So here we have a schematic of a vessel with a width of w, a length of w, and a height of h. Furthermore, we're going to assume that the density varies as follows. So the density is given by the function rho naught minus kz, where k is a constant. So what this tells us is as we increase position in the z direction, so as we move up, the density will decrease from its reference density of rho naught. So let's calculate the total mass of the fluid given the knowledge of the density function given here. So recall that the total mass will be equal to the density integrated over the volume. So we can substitute what we know. So in the z direction, we would integrate from 0 to h. In the x direction, we can go from 0 to w. And similarly, in the y direction, we can go from 0 to w. Our density function is rho naught minus kz. And we will integrate over dx, dy, and dz. So the nice thing here is that we can split up this integral. And so we know that rho naught is a constant, as is k. So we can just say that rho naught is being multiplied by the integral from 0 to h, 0 to w, and 0 to w of dx, dy, dz, minus, and then we can take the k out of the integral as well, because it is a constant. So we are left with 0 to h, the integral from 0 to w, and 0 to w of z, dx, dy, dz. All right, so looking at the leftmost term, we have the integral from 0 to w of dx, so that'll just be w. Right, so the integral of dx is just x, evaluated between 0 and w, so we're just left with w. Similarly, the integral of dy, evaluated between 0 and w, will be just w. And then finally, the integral from 0 to h of dz, it will just be z, evaluated from 0 to h, so that's just h. So what we have here, we have rho naught multiplied by w squared h. And this here is just your volume. All right, so next we have the second term. And so what we can do here, we have, again, we can split up these integrals here, so we can just do 0 to w, 0 to w of dx, dy, and then multiplied by the integral of z dz evaluated between 0 and h. So continuing up here, we have rho naught omega squared h minus k, and now again the integral of dx is just x evaluated between 0 and w, so that just results in w, and the same result for the integral of dy, so we'll have w squared, then multiplied by the integral of z dz, which is z squared over 2. And this will be evaluated between 0 and h. So this just becomes h squared over 2. And this is what we're looking for. So this is our expression. My apologies. This is our expression for the total mass in this volume defined by WWH, given a density function of this form over here. We can also answer the question of what are the units of k. So k is a constant within our function for the density. So our density is given by rho naught minus kz. So remember from dimensional homogeneity that the left-hand side must be equal to the right-hand side in terms of its dimensions. Rho naught can be considered as a initial or a boundary density. So rho naught and rho will have the same units. And similarly, these, since we are adding everything up here, the rightmost term, kz, must have dimensions that are equal to the dimensions of a density. So for a density, what we have mass per unit volume, so that will be L to the negative 3, and that must be equal to the dimensions of k, which are unknown so far, multiplied by the dimensions of z, which are just length. So solving for the dimensions of k, we find that they are equal to m L to the negative 4. That is a mass divided by a length to the power 4. And again, this is found by enforcing the fact that the dimensions of rho must be equal to the dimensions of rho naught and must be equal to the dimensions of k multiplied by z. We must be adding apples to apples. So this is an example of the application of dimensional homogeneity. Next, we turn our attention to two more important concepts and properties in fluid mechanics. These are the specific weight and specific gravity. The specific weight is defined as the weight of the fluid per unit volume. We know that the weight, which has units of force, is equal to the mass times the gravitational acceleration. So given that the specific weight is the weight per unit volume, the specific weight given by the variable gamma is equal to the weight divided by the volume, or mg divided by v. We note that m divided by v is just the density. So the specific weight is given by the density multiplied by the gravitational acceleration. So many fluids will be described by their specific weight. These are widely tabulated in textbooks and tables that you can find online. In SI units, the specific weight has the units of newtons per meter cubed. Next, we turn our attention to specific gravity. The specific gravity of a fluid is defined as the ratio of the fluid's density relative to the density of water at a specific temperature. And by convention, the temperature chosen for water is 4 degrees Celsius. So the specific gravity is the ratio of the density of the fluid in question divided by the density of water at 4 degrees Celsius. Mathematically, we state that the specific gravity is given by rho, the density of the fluid, and that can be a gas or a liquid, it doesn't matter, divided by the density of water at 4 degrees Celsius. So the specific gravity has no dimensions. It is dimensionless. The density of water at 4 degrees Celsius is 1,000 kilograms per meter cubed. And note that the specific gravity does not depend on the system of units employed. So whether we are dividing the densities in imperial units or in SI units, the specific gravity, the ratio of these two densities will remain the same. The next concept that we will explore at a high level is the idea of surface tension. Cohesive forces exist between molecules within a fluid. That is, liquid molecules inside of the fluid mass are attracted to each other equally. However, at the interface between a liquid and a gas, or between two immiscible liquids, there is a force imbalance along the surface, causing it to behave as a membrane. And this is where the concept of surface tension becomes important. So the surface tension, given by sigma, is the adhesive force per unit length. We see this in droplets, or the free surface of a liquid. So here we're showing a liquid, and its free surface is exposed to atmosphere. So this little symbol here, this inverted triangle, indicates that we have atmospheric pressure at this boundary. So this particle here, inside the fluid, has balanced molecular forces. Whereas the particle at the free surface has an imbalance of forces, which causes the fluid at that interface to behave as a membrane. In SI units, sigma has units of newtons per meter. And this makes sense because we are saying that it is an adhesive force which has units of newtons in SI per unit length, m. So if we consider a droplet, what we are saying here is that there is a molecular force along its length. So the surface tension acts along the edge of the droplet, with the total force being 2 pi r multiplied by sigma. Okay, so we have a radius of r, and so this free body diagram would also require us to show a pressure acting on this half of the droplet. So we can write here a pressure. We could define it as delta P. So a pressure is a force per unit area, so we need to multiply it by the area, which would be pi r squared. Okay, so the surface tension force is given by 2 pi r multiplied by sigma. And again, this makes sense. The 2 pi r gives us a length, which is the circumference of that circle. So that's length multiplied by dimensions of newtons per length. So what we are left with is dimensions or units of newtons. So the surface tension force must be balanced by the pressure differential between the inside and the outside of the droplet. So what this means is that the surface tension force, given by this, must be balanced by the internal and the external pressure. We can write this as delta P is equal to Pi minus Pe, so the internal minus the external pressure is equal to 2 multiplied by the surface tension divided by the radius of the drop, r. And this suggests that the pressure inside the drop must be greater than the pressure external to the drop in order for all the forces to be balanced. Now, the concept of surface tension is quite involved, and we will not explore this too much in this course, but it is good for you to be aware of the existence of these surface forces at the interface between a liquid and a gas.